So we'll wait for a few minutes more before we begin.
Right.
Pawan, is that your daughter? Yogyata or Yogita, whatever.
Yeah, she's there in Japan.
Hi, Mr. Sunil. Hi.
So we'll wait for a few minutes more before we begin. Yeah, we'll wait for just a few minutes more. 3 o'clock.
Hi, Mr. Sunil. Hi.
Hi.
Hello, guys. Mr. Malhotra.
Hi, Subbu. Good to see you. Rather, we still can't see you, of course.
Can't see me?
I think your camera may be
I
off.
can't see you, Subbu. I don't want to see you also, but hi.
Okay.
If I can tolerate you, you should be able to tolerate me.
Hi, Professor Lok. Welcome.
Hello, Chandru. Good afternoon.
Good afternoon. Let me just put on the camera. Let's see if it works.
Just a few minutes more. We already have 36 participants who have come
Malhotra
in.
Sahab is pretty famous.
Yeah. So we just wait for a few more minutes.
Malhotra Sahab, आप बात भी नहीं कर रहे, इतना serious क्यों बैठे हो?
नहीं, I have muted myself. यार, static आता है बहुत.
अच्छा फिर बोलेंगे कैसे साले तू म्यूट रहे
नहीं वो बाकी लोग बोलेगा ना मैं थोड़ी कुछ बोलेगा
anyway. Okay. Yeah. Hello, Vikram. Good afternoon. Good to see you.
Good afternoon.
Good afternoon.
Good afternoon.
Good afternoon, sirs and ma'am.
Good afternoon, everybody. It's very nice to see a lot of participation. I can see from overseas.
Yeah.
It's very heartening to see that.
Great to have guys.
Warm welcome to all of you. Yeah.
Thank you, sir.
Few more minutes and then we begin.
I can see Chandru finally.
Who's
My
that?
day is not made. My day is spoiled.
Who said that? Is it Pramod?
Okay.
Right. I think 1 minute and we can start. People
Sure.
are joining.
Sure, we can start.
And while we are
Yogita,
on, yeah, sorry.
Yogita, can I request you when we start to just keep everybody on mute?
Yeah.
And Mr. Malhotra and myself will unmute ourselves, you know. Okay, so Yogita, can you hear me?
Yeah, very well, very well. I
Okay.
think we can start. Good afternoon, everyone. And it's 6:30, and I think it's we'll start. A lot of people are already here.
6:30 in Japan, right?
I'm sorry. Yes, 6:30 in Japan and 3 p.m. in India. Sorry. So I think we are ready to start. Please, Mr. Pawan Kapoor, over to you. Thanks.
Thank you, Yogita. And at the outset, a very warm welcome to all of you this afternoon for this session on engine layouts and propeller selection. We have a guest speaker, Mr. Rajesh Malhotra, with us today. Some of you may be aware that we have been conducting a Learn from the Practitioner series programs for last close to about 8 months, and which was launched last year during the pandemic itself. And that has been a very successful series. We have actually launched a program in shipbuilding, um, ship repairs, and dry docking, which consists of 4 modules, very extensive modules. And in fact, they are programs which run over 2.5 months, generally run on the weekends, but they include a lot of assessments, assignments. They are comprehensive program intended to actually develop the skills of people from marine engineering background or otherwise in the area of ship building, the entire process, which includes the engineering aspects of shipbuilding, materials and processes. We also have extensive modules on dry docking and repairs. So while those programs are extensive, we also felt the need to have shorter programs, which could be of half a day or 1 day duration, but on topics which are very much required by the industry. So with this as a thought, we requested one of our practitioners, Mr. Rajesh Malhotra, to take up a topic which was close to his heart, and he chose engine layouts and propeller selection. So today, actually, this webinar also becomes, I would say, a launch day for our short-term technical series. Mr. Malhotra, at the end of his discussions, will also have an open talk with all of you to try and understand what could be the areas that the industry requires, for competence building in various aspects. So with that, I would, before I introduce Mr. Malhotra to all of you, of course, some of us who are his classmates know him very well, but for the other people who are there in this program, I would just like to tell you briefly about the ISF group itself. We founded in the year 2000, and it was initially a charitable trust, Inner Search Foundation, which we had founded. Which has expanded over the years to now do a lot of research activities. Although initially the idea was yoga, meditation, personality development, and so on and so forth. In the year 2004, we launched our maritime services companies, and under them we do a host of activities which include value addition training programs, learn from practitioner series programs. We have distance learning programs for various ranks who are serving on board ships. We also have a division which is entirely focused on developing digital solutions. And as you can see, our focus largely is on digital solutions which are meant for, which support training and education. Then we also provide academic partnerships to some established institutions, and we are closely working with the National Union of Seafarers of India in providing them support for their skill development centers. We have a division focused on surveys and audits. And lastly, we have an HR services division, which is more into placement and other kind of support services that the industry requires. So that's briefly about the ISF group. My name is Pawan Kapoor, and it's my pleasure now to introduce Mr. Rajesh Malhotra to all of you. So the topic, as I said, is engine layouts and propeller selection. Mr. Malhotra graduated from the Directorate of Marine Engineering Training in the year 1980. And after sailing for almost 14 years, he has spent close to 12 years plus in the shipyards and dry docks, where he was involved in ship designing, ship construction, ship repairs, project management, and warranty claims, and so on and so forth. He understands the entire gamut of activities which go on in the shipbuilding and repair industry. And subsequently, he took up training, and he has spent last more than 5 years actually in actively training marine engineers and other ranks within the industry. So without taking much time, I'm going to hand over the stage to Mr. Malhotra, and will request him to share the agenda for the day and then start his session. Gentlemen, we intend having a break after about half an hour of his discussions, so that you'll have a chance to ask questions. And we'll have one more break towards the end. So in case you have any questions, feel free to put them on the chat box. For those of you who are not on Zoom but have entered through YouTube, I could request you to put your comments or any questions in the YouTube, chat. So our admin team will pick that up and we'll share it with Mr. Malhotra. And we hope that before we end the day's session, we should be able to answer most of your queries. So with that, without taking much time, Rajesh, it's over to you. And thank you very much.
Thank you, Pawan, and good afternoon, gentlemen and lady.
Good afternoon, sir.
I will start with the topic for the day. I mean, thank you, Pawan, for the very, gracious introduction. I hope I live up to everyone's expectations. Now, the agenda for today actually is, or as Pawan had suggested, why did we start this whole thing? Is actually the first point, the importance of in-depth technical knowledge in performing technical managerial functions. See, I am in the minority camp. The majority actually thinks that management is all about management and finding the right person to do the right job. And they are probably correct. But I am in the minority camp that believes that a very sound technical knowledge and grounding is the hallmark of a good technical manager. Now, over the years, my belief has only, been reinforced. And I will just talk about two incidents. One is very recent, in fact, 1.5 months ago, when we were conducting the course for the dry docking and repairs. And one of the participants there actually told us about the experience he had when he was trying to plug boiler tubes. Water tube boiler, the manufacturer was Gangram boilers. And unfortunately, they were not very forthcoming in how the tubes are to be plugged. And, he was pretty much on his own. And unfortunately, he did not breach the tube that was plugged, which is required to be done to prevent pressure buildup in the tube, because otherwise sometimes the tube explodes and damages the tubes around it. Now, fine. He said he was not lucky, and he did have this experience where the other tubes also got damaged. So that only was reinforcing my belief that to be a good technical manager, you must have sound technical knowledge. The other incident actually happened much earlier. In fact, sometime around 2006. And that was a much more significant incident, which with commercial implications. I was the project manager for a diving support vessel. This is a dynamic positioning DP2 vessel. And everything was going fine. The sea trials were done. But during the sea trials, a big hitch was faced. And I was not, although I was the project manager for that vessel, I was not the sea trial manager for that vessel. And so I was actually not really aware of the problem they had faced during the sea trial. But I was called into a big meeting in our office. This is a big boardroom where the owner of the shipyard was there, the ship owners' representatives were there, the vendors were there. The vendors happened to be Alstom and Rolls-Royce. And then, of course, class was there. ABS, the country manager was there, who will probably watch for this. And so the issue there was, I was told, Rajesh, you please start preparing for taking the vessel to Dubai without handing it over to the owners. We will take it as a shipyard property and under shipyard supervision. The issue was that during the trials, what happened was, there was a trial which was supposed to be done that after the blackout, the thrusters needed to restart automatically. This was not happening. And so obviously the vessel could not pass the sea trials. And so the question was, how was this to be rectified? Now the issue was that Rolls-Royce had put plus minus 10 volt signals in all their thruster controls. And these needed to be changed to 4 to 20 milliamp signals. I won't go into the technical reasons for that, but that is what actually needed to be done. And since they were not really aware of the number of signals that need to be changed and how much time it would take, it is much better and much easier to work on the vessel in Dubai. I mean, you can get whatever parts you want. It's much easier in all respects. So a decision had been taken that the vessel would sail to Dubai as a shipyard under the control of the shipyard, with shipyard crew manning it. And there she would, go through all these modifications, and then the ship would be handed over to the owners. So the moment I heard this, I opened my mouth, sir, but, my boss just cut me off. He says, Rajesh, this is not a technical problem. This is you please look into how we are going to take the ship to Dubai and let's sort it. I said, sir, would you please hear me out? So then they heard me out. Now the issue is on a DP2 vessel, the first thing is that the whole logic of the thing, the FEMA, the way the failure mode effect analysis is done, there should never be a blackout on a vessel which is DP2, because that affects the divers who are down, and obviously you can't risk their lives. So blackout is out of question on a vessel like this. So the requirement for the thrusters to restart after a blackout is not really, or was not really, a class requirement. Neither was it a requirement of the specs that we had signed, the new building contract that we had signed. And it was just that in the sea trial protocol, Alstom had included this test because this is normally what is the status on, or this is what is normally done in most of the DP2 vessels, that the thrusters restart in case there is a blackout. But the whole logic of a DP2 vessel is there should never be a blackout. So this was not a class requirement. It was not a requirement for. So then everyone said, okay. And since ABS was there, you know how class is. They are very non-committal about all this. They told me there that, okay, Mr. Malhotra, you please put up a proposal of what you intend to do, and we will see if it can be done. So what I did was I left the meeting. I came down to my room. I put out an email to the vendors and to class saying that they need to modify the trial protocol to remove this test that the thrusters must restart after a blackout. And it took about 3 days or maybe 4 days. I can't remember how many days it actually took. Finally, class, and of course, the owners, of course, agreed because there was nothing in the spec that said that the thrusters must restart after a blackout. So everything was approved. A new sea trial protocol was approved by class, owners, and everyone in question. And this did not contain this particular test. And because it had already done all the other tests, the certificates for this vessel were issued, and the vessel was delivered to the owners in Bombay itself, and it sailed out from Bombay under their own flag, mostly without sea. So this is just to tell you that, technical knowledge does sometimes make a big difference. And although class and all are supposed to be helping you, sometimes for whatever reasons, they maybe don't come out with the right answers. Anyway, fine. So that is the background of this. I will be covering concepts of propeller design and concepts related to engine layout, etc. I hope I cover them. And then actually we'll come to, like Pawan said, that, this is what we have in mind. I mean, we need, or we believe that, technical managers must have good technical knowledge. And it's our aim to try and enhance this knowledge. What the industry requires is what we need to know. And I hope we have a discussion on this at the end of the thing. So now coming to the topic in hand, to go over the fundamentals actually. See, the starting point for the power requirements of any vessel and for the propeller design points of any vessel is always the speed that the designed vessel needs to achieve in service. That is always the starting point. So whenever there is a new vessel to be designed, actually, what is done is the vessel has to undergo a model test to validate the power and the speed requirements and the propeller design. During this model test, actually, the vessel is towed at various speeds that correspond to basically the service speeds that are required to be achieved. And recordings are done for the resistance that the vessel encounters. Now, that is what we actually call the towing resistance of the vessel, which is given by the frictional resistance, the residual resistance, and the resistance given by air resistance. The residual resistance actually comprises of two parts, which is wave resistance and eddy current resistance. Now, as I will be talking about in the next slide, the proportion of the resistance is actually to a large extent are going to depend on the speed. Okay. Now, so the corresponding effective towing power, which is required to move the ship through water at a speed of V, is then given by V into this towing resistance, which is actually the force. So force into velocity. And because this towing resistance is normally, actually, it depends on a whole lot of factors, but is normally, near to the square of the velocity itself, you will have this equation that the power requirement is proportional to V cube. And you will note from this that all the curves plotted of power versus the velocity will always be hyperboles. They will never be straight lines. We will come to that a bit later, but this is where we start. These are what the fundamentals are. Okay. Now we come to the proportions of, the various resistances depending on the speed of the vessel. And this is where it becomes very clear that as the speed of the vessel rises, the proportion of the wave and eddy current friction rises disproportionately. And that is why the speed of the vessel is central to any discussion on power and propeller design. Because we need to, for very high speed vessels, you are aware, like you have hydrofoil, the whole craft, and the propeller, your hull design needs to be totally different. There, because they are high speed. And in a high speed vessel, what is going to happen? The wave resistance is going to increase exponentially. As you can see, in a low speed vessel, the frictional resistance actually forms 90%, while in a high speed vessel, the frictional resistance is 45%. And the wave resistance that changes dramatically as the speed of the vessel increases. Now, this leads to something called a wave wall. Actually, if you see what happens here is if I increase the speed of my vessel, believe me, this is an actual 600 TEU container vessel. And for a speed of 15 knots, the power requirement is only about 2,800 bhp or kilowatts rather. And if I increase the speed to 17.8 knots, that is just an increase of 2.8 knots, the power requirement is almost going to double. The power requirement doubles. And if I increase it closer to 20 knots, I mean, even higher than 70.5 knots, what will happen is no amount of increase in power is going to increase the speed of the vessel. This is known as the wave wall barrier to ship speed. And the only way then, actually, to increase the speed of the vessel is to change the hull design, or what is known as the lines of the vessel. The underwater design of the vessel needs to be modified if you want to actually increase the speed, because what is happening here is that whatever power or whatever velocity that you increase, the additional power is just going to overcome the wave resistance. It is not adding to the velocity of the vessel. And this is, this is important because we realize that the lines of the vessel, the propeller design, everything needs to change if we want to increase the speed of the vessel without a corresponding increase in power. Okay, so this is what this slide is showing. And please note from here that the power, that is the kilowatts, which is on the y-axis, and the speed of here it's the speed of the vessel. In certain cases, you will find it's the RPM of the engine. We will come to that thing. But this line, it's not a straight line. It's a curved line. It's a hyperbole. So wherever you see straight lines, we need to realize that they're actually using log scales. They are not using, because if power is proportional to V cube, you will always get a curved line like this, right? So coming back, just to recap what we've seen so far, in general, all resistances are proportional to the square of the speed of the vessel. Okay. And however, for higher speeds, the wave resistance is going to increase much faster and you're going to reach something which is called a wave wall. If the speed of a vessel originally designed for 15 knots is increased to 70.6 knots without change of the hull design, the power requirement is almost going to double, because that is the effect the wave wall or the wave resistance has on your vessel. Okay, so this is a recap of what I've just told you. Now coming to the slide where we put together, see, the thing is that there is a relationship between the vessel speed, the ship's velocity, the propeller velocity, and the RPM of the engine. In the case of a fixed pitch propeller connected to a reversible engine, and we are all aware of this relationship actually, but this drawing just gives it to you, that if you see the velocity of the propeller is proportional to the RPM of the engine, proportional to speed. The RPM, sorry, not the speed. The velocity is proportional to the RPM, because the pitch of the propeller in the case of a fixed pitch propeller remains fixed. So this is important to remember, because this is what you need to remember. What is the relationship between the ship speed, the propeller speed, and the RPM of the engine? This is where it all comes together. The relationship between the ship speed and the propeller speed is what we normally call slip, right? That is the relationship between the ship speed and the propeller speed. And now I come to something which happens while the ship is, see, you must, what happens is during the propeller model testing and during the sea trials, the condition of the hull and the propeller is that they are normally completely clean and smooth. There's no fouling on them. And also the condition of the sea during the trials is always that calm sea. I mean, we always choose calm sea. No one does sea trials in sea of Beaufort more than 3. So this is what the situation is. But in actual service, what is going to happen is that the hull is going to get fouled, the propeller is going to get fouled, you're going to get rough weather. Now, fouling and rough weather both have a certain effect on the ship speed, on the propeller speed, and obviously then the power developed by the engine. Now, the general thing is what happens to this curve. Let me just go back here. Sorry. Okay, I need to go all the way back here. What happens to this curve in rough weather and when your hull is fouled and your propeller is fouled is that this curve is going to move to my left. That means to maintain the same RPM, I would need to require higher power. Or if I'm delivering the same power, then the RPM is going to drop. That is what happens in rough weather or when your propeller and hull get fouled. This is important to remember, that the curve is going to move to the left, because a ship with fouled hull will consequently be subject to extra resistance, which will give rise to what is known as heavy propeller running conditions. That is, the same propeller power, the rate of revolutions will be lower, or to maintain the rate of revolutions, you would need to deliver a higher power. Okay, and whether it is rough sea or it is fouling, the effect on the propeller, ship speed, and engine are identical. So these are actually treated as, identical, or we treat them the same way. Right. Now, this is a slide. I will not, because to explain this slide would really actually take a lot of time. But those of you who are interested can actually go through this later. But here it shows you the effect of what happens to the ship's performance when it is sailing to rough seas. Right? At 100% power, if you're getting 15 knots, you would actually need to deliver 115% power to get those 15 knots in rough weather. This is what is meant by a sea margin also. Right? Then see, it does not only affect the ship speed, it also affects the propeller. The effect it has on the propeller is that it shifts the propeller curve to the left. By the way, all the curves that you're seeing here are straight lines. That is because, as you can see somewhere, they've written at the bottom that logarithmic scales have been used. So wherever you see straight lines for propeller curves, you have to remember that they have used a logarithmic scale. It's only on a logarithmic scale that a propeller curve will appear as a straight line, because we find it easier to deliver, to deal with straight lines. At least I find it easy to, deal with straight lines. We always prefer to use log scales. Okay. And then, of course, this is introducing another concept here. The last slide on my right, or the last drawing on my right, introduces the concept of light running and heavy running propeller. As you can see, the heavy running propeller curve is on the left of the light running propeller curve. And the difference between these two, I will come to that, is what is known as the light running margin. It is what is known as the light running margin. Because you must remember, from the sea trials, the model test, everything, we have got the light running curve of the propeller. We don't have the heavy running curve of the propeller. We have a light running curve, but we will assume a margin of 3 to 7%, and we will shift this curve to the left, and we will do all our designing on the heavy running curve. That is what is done practically. Otherwise, in practice, when the ship is in service, we would not get the results as desired by the owners. Right. So I will leave this slide here, but I can, when we do a more detailed course, there is a more detailed explanation for this slide, how it is all happening, how it is all shifting, and how, if you note from the middle slide, the slip. That is the difference between the propeller's speed and the vessel speed. Actually, that is what we call slip. And this slide I've just, used, these are actual results from Lloyd's, where they have actually plotted these power curves on a container vessel. And, depending on various weather conditions, extremely wet weather conditions, where you had apparent slip of 6%, average weather conditions where you had, 3% slip, extremely good weather conditions where there was no slip, and in some cases you even had a negative slip. But the only reason, and this is between the BHP, that's the power of the vessel, and your propeller RPM. This is how you will see most of these curves and propeller layouts, etc., etc. You'll see them on an axis of power, and you'll see them on an axis of propeller speed, RPM. The relationship between the propeller speed and the engine RPM is direct, because it's a directly coupled propeller, fixed pitch propeller. Okay, and the constant there is your pitch of the propeller. Now, the reason I put this slide here to impress that actually all these lines would be curves, but we will be actually from here on dealing with straight lines, because we are going to use log scales. Okay, now we actually come to part of the topic for the day, what are engine layout and load diagrams. Actually, the power produced by any engine, any given engine, actually depends on a constant. You all know the formula plan, actually. The constant here is your stroke length and bore, and your mean effective pressure and the RPM. So the two variables in this formula are your mean effective pressure and the RPM. Now, the engine manufacturer has the freedom, actually, from a given engine to change both these parameters depending on the kind of service the owner wants. He can either change the mean effective pressure, that would change your power, keep the RPM the same, or he could change the RPM. Obviously, lower RPMs are preferred, especially nowadays where, your propeller efficiencies, other things, a lot of things depend on having a lower propeller RPM. So you would like to have a lower propeller RPM, but in that case, to achieve the same power, you would need to actually increase your mean effective pressure. Now, also, as per the propeller law, for engines coupled to a fixed pitch propeller, your brake horsepower is a constant multiplied by N cube. That is your RPM cube. So that will be a hyperbolic curve. Your engine is actually directly proportional to the RPM. Your propeller is actually proportional to the cube of the RPM. So in general, what we can say is that the power is equal to a constant into n raised to I, where I can vary from, say, 0 to 3 to 4, whatever it is you want. Okay. But if I use a log scale, then it becomes a straight line. Y is equal to mx plus c. That is what it becomes. So whatever was the parenthesis there, I, it would actually come as a constant here. Not as a constant, it would come as a, as a figure for your x, actually. Or, it would come as a here. So this is what it is. We are going to use straight lines and linear scales. The reason being, it's easier to work with them, at least for me. And what you must understand here is when I is equal to 0, that is n raised to 0, you would get a straight line parallel to the x-axis. When I is equal to 1, you would get a straight line parallel to the line shown there. When I is equal to 2, you would get a straight line parallel to the line shown as I is equal to 2. And when I is equal to 3, you would get a straight line parallel to I is equal to 3. So the point here is that your propeller curve will actually be parallel to the line I is equal to 3 because it is n raised to 3. And your engine power curve would be parallel to the line I is equal to 1 because in our plan equation, it is n raised to 1. This is what is the important when we start using log scales. This is how we get the lines. Which line is parallel to which one? You must remember that. Your propeller line will always be parallel to I is equal to 3 generally, though it may be somewhere between 2 and 3. That is fine. And your important thing is that your engine line will always be parallel to I equal to 1. That is what it is, because in your formula plan, n is raised to 1, right? Now we come to actual engine layouts. Now, okay, before I actually start on the layout, let me explain something to you about MAN BMW, the way they number the engines. For example, this is MAN BMW S70 MC, dash C 8.2 tire 2. Okay, so basically anything and everything to do with this power, with the power of the engine, is actually in the specification of the engine. S is a super long stroke engine. We all, if you look up your manual, you will come to know what is the stroke bore ratio of your engine. S denotes a certain stroke bore ratio. Okay, now 70 is the bore of your engine. So this is where we get the length and the area in your plan formula. N is you get from these layout drawings, whatever is your RPM. In this case, for this particular engine that they are showing, the maximum RPM is 91. And that is where you would get the maximum power. And but you could also have an engine which will operate at 77 RPM. So the RPM is known, the stroke length is known, the area is known. The only thing that is missing is the MEP. And if you can see here, it says MEP at the point L1 is 20 bar, mean effective pressure. And that is actually also there in your specification. The number 8, the number after that, MCC8. Actually, you could have MEC8 also. But irrespective, that would be an electronic engine. But the number there, 8, is known as the Mach number. And there are components of your engine also which are denoted by their Mach numbers. For example, your main bearings are denoted by a Mach 8 bearing or a Mach 6 bearing. The reason being, it is designed for a particular MEP. That is why your Mach number is so important. That 0.2 is known as the version number, but version numbers are not, you need to look up your manual to actually find out what that version number means. Generally, if it is 0.1 or 0.2, it generally means a Tier 2 engine, but they mentioned that at the end of the specification also. But the important thing is that the MEP is there in your Mach number, and MEP is very important. See, if I look at an engine layout drawing like this, if you take the parallel lines, L3, L4, L1, L2, these parallel lines are your constant RPM lines. Okay, so in this case, your constant RPM is either 77 or I mean, it can be anywhere between these two, but those are the limits, 77 to 91. That is what your RPM limits are. The lines L1 and L3 and L2 and L4, they are constant MEP lines. They are constant MEP lines, and they are parallel to what we saw here, parallel to I is equal to 1. These constant MEP lines are parallel to I is equal to 1. That means the MEP at L1 is 20 bar. The MEP at L2, the MEP at L3 is also 20 bar. L2 and L4, the MEPs would be about 80% of 20. So 80% of 20 would be about 16 bar. So L2 and L4 both have constant MEPs, but the power developed by the engine is going to, although the MEP is constant, the power is going to change because of the RPM changing. So this is what is known as an engine layout diagram. As you can see, at point L1, the power produced by this engine is 3,270 kilowatts per cylinder. And point L1 is known as the nominal continuous, maximum continuous rating. Nominal MCR is what your point L1 is known as. See, all my engine components are designed for point L1. But you must remember, the way the propeller is going to be matched to your engine, the engine cannot operate at point L1, because at point L1, there are absolutely no margins left. The propeller has to be matched to the engine somewhere between this trapezoid, parallelogram. It has to be matched somewhere inside this parallelogram. It cannot be matched at the extremes. It has to be somewhere in the middle, because then only you get sufficient margins, what is known as C margins, what is known as engine margins. Then only you will get these margins if the propeller is matched to the engine somewhere in the middle. It cannot be matched at the nominal L1. So for all, okay, you may ask then what is going to change in the engine? If my engine is designed to deliver L1, that is 3,270 kilowatts, if I choose a lower power, like for instance, at point L3, only 2,770 is being delivered. And at point L2, 2,610 is being delivered, and somewhere in between is going to be somewhere in between all this. So, what changes in the engine then? What is going to change? See, because power produced by engine depends only on the fuel and the air. What is going to change in your engine is your fuel equipment and your turbocharger. These two are going to change in the engine when you select, you have to select a low power. I mean, if you see, practically all engines are derated. They will never operate at the nominal SMCR, which is point L1. They will never ever operate there, because then you would ruin your engine in a very, very short time. There would be no margins left, right? So this is what a typical engine layout looks like. And MAN BMW gives you this for all your engines. Okay, and if you see from this and the next slide, actually, if you see what is happening here, that the MEP normally is between 80% and 100%. That means the difference between lines L1, L3, and L2, L4 is normally about 20%. But the RPM actually varies in a range from 79%. If you see the first engine itself, it is 79% to 100%. But in certain cases, it can even be, 87.5%, 92%. I'll show you those engines. Yeah, if you see the engine at the right here, the RPM is actually 92% only. That means the difference between the minimum RPM, maximum RPM is only 8%. And in the last engine, it is in fact only 7%, which that engine is K98ME C7.1. So for all your engines, you have layout drawings like this. It is the job of the designer and the, the shipyard actually to select the propeller operating point, which is within this engine layout diagram. That is what it is. So, right, at this stage, I can take a short break and I can take questions or, yeah. So Pawan or Yogyata, please come in if there are any questions or if anyone has any questions.
Yeah, thanks, Rajesh. Ladies and gentlemen, in case you have any questions, you may please unmute yourself or raise your hand, and then we will request you to raise your question so that Mr. Malhotra can address it, please.
Boy, either I'm being very clear or I'm not being clear at all.
No, I think it's going fine. If we can just wait for another minute, if there are no questions, we can resume and then see if there are anything coming.
We can take a short break, Rajesh, maybe a glass of water or something, and then we can resume.
Yeah.
Yeah, please. Gentlemen, please feel free, ladies, to raise your questions.
Should I continue?
Yeah. If there are no questions, Rajesh, we can continue. Then we can stop towards the end for any questions, please. Yeah. Okay.
Right. Now, actually, we come to combining the ship's propulsion point to the engine layout drawing. Now, like I mentioned earlier, what we are going to get actually from the model testing is the light running line of the propeller. So if you can see here, what I will get is my propeller design point shown as PD, which is on line 6, which is a light running line of the propeller. And here, if you see, the light running margin is shown as 5%. Normally, these margins are 3 to 7%. And in certain cases, for example, in icebreakers, etc., these margins could be as high as 18%. Why? Because that ship is going to operate against a lot of resistance. It's going to break ice. So this heavy running margin needs to be built into the propeller design, right? So my propeller design point actually, without any margins for a clean hull and calm sea, is going to be point PD on what is known as my light running line. Here, okay, let me go into what is light running and heavy running right here so that everyone's clear about how these lines come about. What is called your light running factor is actually a light running RPM minus the heavy running RPM divided by the heavy running RPM multiplied by 100. And like I've been saying earlier, that this is normally between 3 to 7. In the middle of the thing, it is 5%. So light running line I have got from my model test. And from my model test and my propeller test. That is from where I've got the light running line. But what I'm going to do is I'm going to draw another line parallel to the light running line, which is line number 2, which has got a light running factor of 5%. Why? Because what happens is, to maintain the RPM of the propeller, when there is heavy sea or there is fouling, I need to deliver more power to the propeller. So that is why I choose a heavy running line. This is known as my heavy, and in fact, when we were doing some of our other courses, people were asking, on some of the ships, what has happened is the propellers got trimmed. The reason why they do this trimming is to improve the heavy running performance of the ship or the heavy running performance of the vessel. So they actually increase the heavy running margin by actually trimming the propeller in service, because they're probably finding that in service, when the vessel is facing rough seas or your hull is fouled and propeller is fouled, it is not performing or the engine is getting overloaded. So that is why this light running margin becomes important. So the first design point actually you get is your point called PD. Now let me go back to that slide now. Here. So PD is your propeller design point, combination of speed and power obtained assuming optimum operating conditions. That is clean hull and good weather, both theoretically and from the tank test. This is the point I'm going to get. And this is where my propeller and engine have to be designed. Actually, but if I do it here, then there are no margins. So what I do is I add a margin, which is called a C margin, which is meant for rough seas. And a 15% margin I add. And the new design point that I get is actually shown as SPD or PD dash. That is my new design point. But I'm going to transfer both these points to my heavy running line, because I'm now in practice now, I'm not going to use line 6 anymore. What I'm always going to use now for a ship in service is my line 2, which is my heavy running propeller line. So both these points are transferred to the heavy running propeller line, and I get my first point, propulsion point, known as SP, which includes a 15% C margin for heavy seas or propeller fouling or hull fouling. All these, and actually speaking, the other term for this point is going to be my continuous service MCR, continuous service rating, CSR point. That is my point SP, which has got a 15% C margin for heavy running and fouling. Now to this point SP, actually, I'm going to add another margin, which is known as my engine margin, which is or the performance for the performance of my engine, because my engine is not going to operate as a new engine all the time. It is going to deteriorate. And once it deteriorates, the power being produced by the engine is going to reduce for whatever reason. We all know the reasons for that. So when I add another 10% engine margin, I arrive at my continuous propulsion point, or MP, what is known as my service MCR, okay, maximum continuous rating, which please note is different from my nominal MCR, which was 0.L1. My new SMCR is actually 0.MP, which includes a C margin of 15%, and it also includes an engine margin of 10%. Okay, so this is how I arrive at my specified MCR. So my engine, whatever engine I buy, and coupled to my propeller will deliver my specified MCR. That is what. So it will be a derated engine which will operate at the SMCR that is required. But my continuous service rating is actually the point SP. That is what my country, and you will find all this on your certificate, especially if it is an NKK certificate. You will find that all your points are, or your MCRs are mentioned, your SMCR is mentioned, and this is what will be actually the brass tally that is put on your engine, will show you the specified MCR. And actually speaking, for that particular engine that I showed you, there's, okay, we'll come to the actual specified MCRs and the continuous service ratings. And right. And the other point here to remember actually is that at which point do you get your most efficient specific fuel oil consumption, because that point is also important for us. The the consumption of oil in the engine is equally important. So is it optimized at SMCR? Generally, no. The specific fuel oil consumption that you get will never be optimal at the MCR. In fact, actually, you will find that on a ME engine, it is 80% of the SMCR. And for a MC engine, it is 70% of the MCR, SMCR. That is where your lowest specific fuel oil consumption is going to be, where your engine is going to be optimized, your fuel consumption is going to be optimized. And this leads to other issues because, when you are going to operate, do slow running and other things, actually, your SFOC may rise. You will not burn fuel optimally, but your total fuel consumption will still come down because you are actually generating lower power. So if you're operating at a point which is just above your blower cut-in points, etc., your total fuel consumption is going to be very low. Where your SFOC is not going to be optimal. It is not optimized at that point. And in ME engines, actually, you can optimize it for high load running and low load running. I mean, ME engines are just brilliant. You can, optimize your engines any way you like, actually. And it is all done on a screen. If you know how to do it, it's always done on a screen. It's not like the MC engines, where I actually need to take spanners and, actually go and change settings on my engine. This is also important, actually, in the context of your new regulations that are going to come, where you need to limit the power for the engine. And ME engines are going to be very easy. Even in the older MC engines, there was always ways you could limit your power. I mean, these are all settings that you do on your controls. And I mean, it's actually cakewalk, actually. Without modifying the engine, you can always limit your power. Right. Right. Now, this is what really, this engine, if you see, actual engine which is used for most of your Panamax vessels, your 8-hatch vessels, bulk carriers. This is the engine that is normally used, 6S, 60 ME, C8.2 and T. Now, this engine, for your 7-hatch Panamax vessels. This engine has a nominal MCR of 14,280 kilowatts at 105 RPM. So this is the point L1, actually, which is your SMCR, nominal MCR. While your SMCR is a specific maximum continuous rating, also referred to as maximum continuous output on an NK certificate, is 9,300 kilowatts at 89 RPM. And this is what is going to be stamped on your engine. What has changed on this engine, actually the engine component-wise is identical to the engine that is producing a nominal MCR of 14,280. What has really changed on this engine is your fuel equipment and your turbochargers. So the maximum continuous, and you can run your ship at 9,300 kilowatts, 89 RPM, continuously without overloading the engine. Okay, this is your specified maximum continuous rating. But the actual continuous service rating, which is also actually marked, but it is not stamped on your engine, but it is given to you on your NK certificate. It is also called your normal continuous rating. It is normally about 7,330 kilowatts at 81.5 RPM. But please remember, you can operate this engine right up to 89 RPM and 9,300 kilowatts. There is nothing to stop you from operating the engine up to your SMCR. Okay. Right. Now we come to the last agenda for the day.
Rajesh, may I interrupt you? There are some
Yeah.
questions which have come up. So I'm just thinking, can we read the questions first and then we can come to this part?
Okay. Yeah.
Okay.
The questions have come up. Just one sec.
Yeah, I think this slide is okay for
Just
that.
put on my headphones so that I can hear them better.
Hello.
Yeah.
Yeah.
Yeah. Hello.
Yeah.
Good afternoon. Yeah. My name is
Yeah.
Elmer.
Yeah. Please go ahead. Please go ahead.
Yeah. How does the what we call the what's the what we call that? Forget. Cavitation affect with the performance of propeller and the what we call ship speed.
How does cavitation affect the?
Yes. Yeah. How does cavitation affect with the propeller performance as well as the ship speed?
Right. See, the thing is, flow through the propeller must be as streamlined as possible. That is the way the hull needs to be designed, and you have so many other, thing. You have the bulbous bar and all, which were meant to actually streamline flows, etc., etc. So when you have cavitation, actually, obviously your flow is not very streamlined. So
Yes,
obviously
yes,
your propeller efficiency is going to drop. The other problem with cavitation is that it is actually going to start damaging your propeller physically. When the air bubbles come and burst on the surface of your propeller, your surface the surface of the propeller is going to become rough. When the surface of the propeller becomes rough, it is the equivalent of, it will increase the heavy running of the propeller. Obviously, the propeller is not going to perform as it was designed to perform.
Yeah, Mr. East, you're on mute. We're not sure if you're responding, but I hope that answers. You can unmute yourself, please. I'm not. Yeah, he's back.
Yeah. Hello.
Yeah,
Mr.
did that?
Ace, does that
Hello?
answer the question?
Yeah.
Okay. Yeah.
Okay.
Yes.
Yeah.
I agree.
Yeah,
Yeah.
we have a question, Rajesh, from Mr. Vinayak Tiwari. How can we decrease the consumption of SFOC?
How can we decrease?
Thank you.
Decrease. Yeah.
Yeah. So, Mr. Tiwari, various ways of decreasing SFOC is. Are you talking with modifications, without modifications?
Yes, sir, with modification.
Okay, with modifications, the biggest modification when you do a derating is you can go in for a completely new propeller. To actually couple it or to design it for the new point that you have in mind. But otherwise, on a lot of engines, to improve SFOC, you have various options with your turbocharger. Actually, where you have these turbocharger bypass design, you have this turbocharger cutout designs. All these are all designed to change your SFOC at lower if you are wanting to operate at lower powers. See, where you have two or three turbochargers, you have turbocharger bypasses, you have turbocharger cutout devices. So these are the ways where with or without modification, SFOC can be reduced. you can't really go beyond beyond the lowest SFOC. And the other things we all know, that you need to maintain your fuel equipment, you need to maintain your scavenge ports need to be smooth and clean, etc., etc.
Yes, sir. So that one.
Yeah, so all those things are, in general, I won't cover those, but if you are going in for modifications, it is either with your turbochargers or with your propeller. Or see, in the earlier days we had something called low speeding nozzles. They are not there anymore. You could go in for a new fuel valve design if you are going to be operating continuously at lower powers. Hello.
Okay, sir. Thank you, sir.
Yeah.
Yeah,
I
thank
mean,
you.
if you are interested in a more detailed answer, I could give you some of it later.
Yes,
If
yes.
you- Right.
Right. I think this is one question which we can tackle in the end. Mr. Balwani has just requested if you can share the service MCR slide again. I'll leave it to you.
Service MCR slide again. Which one does he want? The last one? This one?
Yeah.
Is it this one?
Mr. Nitin, you can just like give us a thumbs up or unmute yourself and let us know which one it is.
Yeah, madam, it was already shown. Thank you very much. I have already.
Okay, cool. Okay, thanks. Yeah. Should we proceed? And if there are more questions coming up, we can take them towards the end.
Yeah, sure. I think just we can take up the discussion on desired topics and then we can come back.
Sorry?
Yeah, we can take the discussion on what topics
okay.
maybe. Yeah.
Right. So, gentlemen, what really we had in mind, see, a lot of details that can be covered about the power develop for the engine, because I did not do it during the course of my discussion. But if I asked someone right now, what is the definition of mean effective pressure and how much of a difference between the mean effective pressure and your mean brake pressure in terms of bar, I'm not sure I would get the right answers. So there are a lot that can be covered when we are discussing power developed by the engine, and that question on SFOC, how do you improve SFOC, balancing power, what do you do first? Whether you adjust the fuel racks first or you adjust the timings first. And how is power balanced? Fuel pump timings. What is the effect of changing timings? Slow steaming without engine modifications, slow steaming with engine modifications, power limiters and your EXXI, fuels, turbocharging effects on power. See, because the MEP of the engine actually depends only on the fuel and the air. There's no other way of changing the MEP of the engine. You need to change the amount of fuel you're burning and how efficiently you're burning it. So turbocharging plays a very important part. Like for example, how do you know how much fuel is to be injected into the engine? It depends on the availability of air. How do you know how much air is available? So turbocharging and its effects on power and emissions, these are the topics. I mean, I would love to go into them. Effect of changing exhaust valve timings. See, no one ever did them on an MC engine for the simple reason that you would have to pick out spanners, hydraulic pump, etc., and go and change the setting of the cam. So no one ever tried to do this on an MC engine. But on an ME engine, this can be done on a screen, a touch screen. And the tragedy of ME engines is that, they can do so much, but the problem is that you need to know which screen to go to, what you do. Suppose I change the timing to earlier opening of the exhaust fan. How does it affect my engine? Or I change my timing to earlier closing of the exhaust valve, will it affect my engine? Won't affect my engine. Turbocharger overall, lubrication, especially in the, in my experience nowadays, there have been a lot of main bearing failures, a lot of stern bearing failures, etc., etc. And cylinder lubrication, another important point, especially with ME engines, we have seen that because the cylinder lubrication adjustments are not done properly during running in. In fact, in my last company, we actually had liners which had to be replaced within the first year of operation. Because engines, because people were not adjusting the cylinder lubrication and not doing the running in properly. Okay, bearing selection, bearing failure, that is already kind of mentioned this, turn bearing, the main bearings. But these are thoughts that I have, or we have rather at ISF. And we would be very interested in listening to what you in the industry would like covered. And we would love to hear suggestions from your end. And more importantly, at what level do you think these should be covered? I mean, they should be covered at the level of the sailing staff, covered at the level of the superintendents. I'm not sure.
Ladies and gentlemen, please feel free to share your thoughts. The aim was to actually have an interactive session to get to know what more industry would need for the present and for the future. So, and if you have any other questions which may be there, of course, there was one comment which came from Mr. Rabi that even Artiflex engines are intelligent engines and they also are capable of modifying the exhaust valve. So I mean, that's right. So essentially,
absolutely,
that is what the intelligent engines are bringing to us. Yeah. Any other questions? Yeah, please. Any questions? Yeah, Prabit.
So I have a question during the trimming of propeller.
Your voice is not very clear. Modak, can you please repeat?
Yes, sir. Can you please tell me about this trimming of propeller? Trimming of propeller.
Trimming, yeah. Yeah, okay. Trimming of propeller, right. That is sometimes done to, to improve the heavy running performance of the propeller. Because what sometimes happens is, see, we've selected a margin of 5%. That is in between the margin we could have selected 3%, 7%. Some people may select a margin of 3%. And then they may find that in actual service, what is happening is the propeller and the engine are not performing too well when they are going through heavy weather. Actually, the next part of this topic was like, how do you make out whether the engine is getting overloaded or not? There are basically two ways in which it gets overloaded. There's a torque. If your torque limiter is, getting activated again and again, your engine is getting overloaded. If the torque limiter is getting activated. The other limiter, of course, is the scavenge limiter. That shouldn't get activated at all. But if your torque limiter is getting activated again and again, it would show, or it would indicate that your engine is actually getting overloaded. So in that case, then you need to change your propeller operation point. And that is sometimes, rather than changing the entire propeller, that is sometimes done, because changing the entire propeller involves a lot of cost. So that is sometimes done. The manufacturer comes and trims the vessel. We had a case like this. I mean, we've actually had people coming from stone manganese, etc., coming and trimming propellers to improve the heavy running performance.
Okay, sir.
There's a question, Rajesh, related to propellers only from Mr. Shankar Ram Swaminathan.
Right.
He's asking how many max number of blades can a propeller have? And can I have a propeller like turbine blades,
Can I have a propeller with?
Having blades almost like a turbine.
So practically it is not not feasible to have so many blades like a turbine. There are, the Void Snyder propellers, etc., have more number of blades. So there is no, but in a single screw, generally fixed pitch propeller coupled to a main engine, we normally go in for 5, 4. That is the normal number of blades. You could, I mean, you could, but then it would change the entire design. Void Snyder, propellers, etc. Yes. Or if you remember the old steamship where they had those turning wheels and also, yes, you do get designs. But what has been actually noted is that the lower up to 3 or 4 blades are fine. I mean, maybe 5. There's nothing to stop you. It would only make your propeller more complicated and probably, add to, and it would actually not, create problem with the streamlining of the flows also.
Okay, Rajesh, we have quite a few questions which have just come up. I'm going to take one by one. One is, of course, from Mr. Simran Singh. Is manganese bronze propeller repairable?
Yeah, propellers are repairable to a large extent. You need to involve class. Actually, yes. In fact, Mr. Atul Mani and all do a complete thing on propeller repairs. Yes, they are repairable. And if since you are talking about the material of the propeller, I don't know if anyone's had stainless steel propellers, but if you have stainless steel propellers, then normally they are on ice class vessels. Please be very careful with your welding machines and welding, because stainless steel propellers will get corroded if your welding machines are not earthed properly. There have been cases where the propeller just disappeared, and it has all been because in service your welding machines on board have not been earthed properly. You need to be very careful when you're doing welding in water when you have a stainless steel propeller. And that's just an aside, since someone's talking about manganese bronze propellers are definitely repairable.
Okay. I hope this meets his requirement. We have Mr. Kshitij Kumar Jain. His question is, can SFOC be decreased by reducing the hull resistance like air lubrication techniques?
Yeah, of course. Anything. See, if you take these hydrofoils and hovercraft, etc., they move on air cushions. So that there was a very interesting video which showed the speed of various things in on land, in water, and in air. And obviously, things move much faster in air because the resistance is much lower. So if the resistance is much lower, the power required to move at a particular speed is going to reduce. And if your power reduces, obviously your SFOC is going to be much better.
Okay. Next question is from Mr. Nitin Balwani. He's asking why cot nozzles not installed on fixed pitch propellers.
Why cot nozzles are not used on fixed pitch propellers?
That's right, yeah.
Cot nozzles are generally used to increase the thrust, and they are generally used more in the offshore industry. The reason why they are not being used, I suppose the savings do not justify the cost of the cot nozzle and the maintenance.
Could it also be that the resistance will tend to go up?
Yeah, I mean, it does not add to the efficiency of the propeller. Okay. It kind of, the cost of the nozzle, the extra material, the resistance, all that, and then actually, then what happens is the distance between the rudder and the propeller is going to change, and you could end up with vibrations, etc. So generally, I have not heard of cot nozzles being used on, but to be honest, I don't know the exact reason. I'm only guessing.
Okay, we have Mr. Ramakrishnan, whose question is that, is there any means of checking the pitch of the propeller when in dry dock?
Yes, it is done. And means of checking the pitch, yes, of course it is done. When you take out the propeller, in fact, when we do the module on propeller repairs, this is shown how you check the pitch of the propeller. Nowadays, you could do it with actually things like lasers and all those.
Okay. There is a comment which has come from Mr. Vikram Gokhale. He says that Becker Mewis duct with fins is being used for large vessels.
Sorry?
There's a specific kind of a Becker Mewis duct with fins.
See, all these are means to improve the propulsive efficiency of the vessel. Yeah.
Okay. Right.
You have contra-rotating propellers. I mean, there's so many of them. So, each of them actually claim to improve the efficiency by 3%, etc., etc. But no one looks at the elephant in the room. The bunkers delivered on board and the way they are measured. Is anyone looking at that? I am not very sure. And you may claim that your efficiency has gone up 3%, but if the losses on your bunkers are more than 3%, how does your efficiency increase, or how does SFOC actually increase? So these are all, till they sort out this problem of bunkers, these increase in efficiencies are going to be all elusive on paper, actually speaking.
Right. Okay. I think we can take one or two more questions. I have a question here from Mr. Vijay Singh. Can we run RT Flex engine with cancel limit? It's a good practice or not, and why? Can we run the RT Flex engine with cancel limit? I think maybe Mr. Vijay Singh.
No, what limit are you cancelling? Is it the torque limiter?
Mr. Vijay Singh, can you unmute yourself and answer this part, please?
Yes, sir. Cancel limit, sir. This is a torque limiter.
Torque limiter. Okay. First, you need to understand why the torque limiter is there. And what will happen if you cancel it? See,
sir, there sometimes bad weather, so RPM reduce. So that's why we cancel the limits, or we maintain the same speed, but more fuel is consumption.
Rajesh, have you heard the question?
No, his audio is gone, I think. Mr. Varadara, your mic is gone. Can you speak?
Sorry.
Yeah, you're back.
Yeah, sorry. Yeah, what I'm saying is, firstly, you need to understand the torque limiter is meant for calm weather. It is not to be used in rough weather. In rough weather, you should be using actually your on your ME engines. It is the rough sea mode is what you should be using. One sec, it is called something else on the ME engines, but on your MC engines, it is the rough sea mode. That is what you should be using in rough weather. See, the difference, let me first explain what is a torque limiter. A torque limiter is something that for a particular RPM, your fuel lever or your fuel being injected into the engine should be limited to a particular amount. See, suppose I'm running at 45 RPM. The fuel cannot go to 100%. Then I'm overloading my engine. That is basically what your torque limiter is. That for any particular RPM you're running at, it limits the amount of fuel that is being delivered to the engine. See, there's no engines. There may be some engines which are fitted with torque measurement, etc. Normal engines are not fitted with torque measurements. So the way a torque limiter works is that for any particular RPM, it limits the amount of fuel. See, why do you have to cancel it in rough weather? It is because when you are trying to run at 90 RPM, with the limiter in place, the fuel is not going. And if the fuel is not going, it will not maintain the 90 RPM. So that is why torque limiter firstly is meant to be used only in calm waters. It's not meant to be used in rough weather. For rough weather, you have the rough sea mode, where the RPM is maintained constant. irrespective, in that case, what happens in the rough sea mode is that the fuel lever can then go to 100% also, even though you may be running at 45 RPM, which is not very nice because your engine does not have, at 45 RPM, I'm sure your engine does not have enough air. And you cannot burn 100% fuel. You'll be ending up damaging a lot of things. So that is why actually in rough sea, it is never a good idea to cancel the torque limiter. Never, ever a good idea to cancel the torque limiter.
Okay.
Okay, thank you so much, sir. Thank you so much.
Yeah.
Okay, Rajesh, I think we'll take a last question now, which I think is quite relevant. Will EEDI requirements affect the light running margin?
See, well, EEDI requirements affect the light run. What will happen in EEDI is that the amount of fuel you can inject, see, basically the power from your engine is only going to depend on the amount of fuel you are going to burn. Given a given engine, given the SFOC, whatever, your power output of an engine only depends on the amount of fuel you burn. So if the amount of fuel that you burn is going to get limited by your EEDI requirements coming into force, then what is going to happen is, obviously, your engine margin and your C margins are going to reduce. Your propeller coupling points have all changed now. So in that case, actually, yes, you could or you would have to go in for things like trimming the propeller or something if you're facing problems with rough sea running. Yes, it will affect your light sea margin, of course.
Mr. Tyagarajan, does this answer your question? Okay. Unless he's muted right now.
So maybe he's asked.
Yeah, he said yes. Yeah, thank you, Mr. Mohan. Thanks for that. So I think maybe we'll close here, Rajesh.
Yeah, but we've not got any suggestions for what they would like.
I think what we can do is, Yogita, we will be circulating some feedback form through that be a part of the agenda, or we can ask people to write to us in that case.
Yeah, we will definitely put in a closing email with where you can put in your feedback. And in any case, on the chat box, I have put in our email address. And we would still like to very much hear from you about the proposed topics. And also, if you have any pending questions that you would still like to ask, and Mr. Malhotra can then probably reply to you on email. So for that also, you can mail us. But definitely, proposed topics is something we would like to hear from you. So do write to us, and our email ID is also in the Zoom automated emails that you have received with the meeting ID link. The same ID is there over there as well. So do write to us, and yeah, I think that's all.
So I think, ladies and gentlemen, we'll bring the session to a close now. First of all, thank you all very much for being here with us today. I hope you have gained from this session to some extent, and we hope to look for to hear from you soon on what else we can do for you. Please watch out for our social media space. I think we have another seminar, of course, not on a technical topic, but around the end of the month, we are having one on, especially in view of the pandemic which is going on. There'll be a topic on a session on building holistic immunity to meet with various challenges in life. And that is our next topic coming up. And feel free to write to us. We are here. Learn from Practitioner series is happening every 3 months. There are sessions on shipbuilding, as I mentioned to you, materials and processes, and of course, ship repair and dry docking. And very soon we'll start launching these smaller programs, which you will hear about, and feel free to enroll for them. They'll be, of course, more like a professional course running, but shorter duration. So with that, on behalf of Mr. Rajesh Malhotra, all the team members of our Learn from Practitioner series, and all the ISF team members, we thank you all very much. Have a good evening and take care of yourself. All the very best. Thank you.
Thank you, Pawan. Thank you.
Thank you very much. Thank you.
Thank you.
That was a pretty nice session. Thank you, guys.
Thank you so much.
Thank you so much.
Thank you, sir.
Thank you, sir.
Thank you so much, sir. Thank you so much. Thank you, sir. Bye, sir.
Thank you.
Thank you, Rajesh ji.
Thank you, Pawan. Thank you, Rajesh.
Thanks. Very useful. Thank you. Thank you very much. Have a good evening.
Right.
Thank you.